Hello, I'm SangBin, a software engineer at Anyscale. Today, I'll present debugging and observability in Ray and Ray applications. So here's things you're going to learn today. You're going to learn challenges and solutions in debugging distributed Ray applications and Ray's monitoring architecture. And at the end of the presentation, I'm going to go over the future roadmap for debugging and monitoring support on top of Ray. So let's start from the brief introduction to Ray. Ray is a general purpose distributed system that makes it easy for developers to build distributed applications. It provides clean and minimalism APIs such as ray.remote, ray.get, and ray.wait. It is also built around very intuitive programming models, tasks and actors, which are corresponding to Python's function and also classes. Let's see an example. So this is an example of ray tasks. As you can see, there's a function f, and just by adding a decorator ray.remote, you can execute this function remotely, and all the distributed system problems are coordinated by Ray. After that, you can asynchronously get the result of the task using ray.get. And in the same way, classes are instantiated remotely using the decorator ray.remote on top of the class. This is called ray actors. Ray actors are useful for stateful computation, and it makes Ray really flexible tool to build various different distributed applications. There are several benefits of using Ray aside from its intuitive APIs. First, Ray is a general purpose system, and it means instead of gluing multiple specialized systems, you can manage a single system. And this doesn't only make it easy to operate complex software that requires large-scale distributed systems, but also helps users to focus on business logic instead of solving problems that require specialized knowledge, such as distributed systems problems. Second, it allows developers to write distributed applications with minimal efforts, since complex distributed system problems such as scaling, resource management, or fault tolerance are coordinated by Ray. And thanks to these benefits, there are many distributed applications written on top of Ray or integrated to Ray. For example, there are native libraries such as rlib, tune, or rayserve, or there are many other community-driven libraries such as integration to Hugging Face, Horovod, or PyTorch, and a lot more. So Ray makes it easy to build distributed applications. Then what's the next challenges? The first problem Ray developers usually face after they start development is to figure out how to debug Ray applications. Unfortunately, debugging distributed systems are really hard, and it is not an exception for Ray. And you usually face this kind of situation. You find a bug and fix it, but there are 2 more bugs and 3 more bugs, etc. And another problem is running them in production. For example, we need to monitor systems so that we can detect anomalies ahead of time. Or when something's broken, we should be able to figure out why it happened. And there are times that there are performance degradation. And in this case, you should be able to understand why performance has been decreased. So, which means you need to understand performance characteristics. So now we are facing the next challenges in developing distributed applications. Debugging and monitoring distributed systems is hard. Let's see why first. Distributed systems are usually learning in really large scale. And it makes it impossible for humans to dig into and fix issues when something's broken. And second, all the components are spread across many different machines in the cluster. And since components are running independently, concurrently, and asynchronously, reasoning the failures or anomalies became much more difficult. Lastly, because failures in distributed systems should be handled gracefully, they are not detected right away, but is discovered later time. Because otherwise the whole system will fail by just a single component failure, which is not desirable. And this is something that Ray users also face when they build distributed applications. This is the inevitable problem. Unfortunately, there are many proven solutions in the industry to debug and monitor distributed systems. And this means Ray can also solve the same problem by supporting the same tools, such as metrics, events, distributed tracing, or the dashboard that shows the stage of the Ray systems. It is also really important to support these tools for both Ray system and Ray distributed applications. And I'll explain why this really matters to Ray. The goal of the Ray is to make it easy to build distributed applications. Since debugging and monitoring is very difficult problem everyone needs to solve when they're building distributed systems, Ray cannot make it really easy to build them if it doesn't provide seamless experiences in debugging and monitoring. That means if debugging becomes easy, it'll help Ray moving one step forward to the goal, make it easy to develop distributed applications. So now it is time to learn how we actually debug and monitor Ray applications. So before we start, let's learn about Ray's programming models first. There are two programming models of Ray. First, Ray's task and actor-based programming, as we saw in the beginning of the slides. This means all the distributed systems operations or interaction will be done as task and actors, which are corresponding to functions and classes respectively. Second, Ray is based off of distributed objects. And Ray's task and actors are sharing data by accessing immutable objects called Ray objects. So Ray is object-based programming. So let's start from what's the typical problems you're facing when you debug task and actor-based applications. This is a typical example code of Ray actors. This code will create an actor that require a single GPU. You can see in the Ray.remote, there's no GPU argument. And after that, you can invoke functions of actors by calling .remote. So you can see c.inc.remote function is going to create the ID1. And each of .remote will produce Ray project. So in this case, ID1, not Ray project, Ray objects. And in this case, ID1, ID2, ID3, they are called object reference, which are referencing to the actual Ray objects staying in the shared memory. Then let's say after the first invocation of increment method, actor is not working as expected. It means actor could be slow, or actor was broken, or something's hanging, or something like that. What would you do in this case? This kind of problem can become really hard when your applications have, for example, like thousands of actors. And to make debugging these scenarios as smooth as possible, Ray is providing three different solutions. First, Ray will increase the visibility of actors and task states. Second, it will give users the ability to add insights to task and actors. Third, it will provide users to add distributed tracing. Let's see the first solution in details. Ray provides the visibility to task and actors from the dashboard. Ray supports a real-time dashboard that helps users debug Ray apps. Especially, Ray focuses on great logical view support, which displays the states of task or actors. Let's actually see the example screenshot. So this is the logical view I captured. As you can see, it gives the visibility to existing actors such as states, resource requirements, lifetime, etc. There's also actor states. You can see everything is currently infeasible. This will help you to notice anomalies in your task and actor-based applications so that you can easily debug issues when something's broken. The second solution is to provide users the power to add custom metrics. Custom metric is the metrics you can record in your application layer. And recording custom metrics in Ray is really simple. You can just import the custom metric API and define the custom metrics, in this case, count. You can see the demo actor's initialization function. And you can record metrics using a record method. So if you look at the ping method, you can see this count custom metrics is recorded every time ping is called. And this will be automatically collected by Ray. So all the metrics will be automatically collected by Ray, and you can import them through Prometheus. Let me briefly explain how to import metrics. You'll also be able to find this information from the document. But Ray automatically generates a file that Prometheus can scrape to. And this allows users to scrape metrics from every node in the cluster. So this file basically is a service discovery file. And you just need to start up the Prometheus with the configuration to scrape this file. And actually, Anyscale product already automatically starts Prometheus and Grafana to scrape metrics when you start up the session. So here's an example. If you click the Grafana button there, you can actually get into the Grafana dashboard. And from there, you'll be able to create your own dashboard that shows the custom metrics. In this case, as you might remember, every actor ping incremented the ping count. And you can actually see the ping count has been increased. I was actually running this script for a pretty long time. So you can see there are 1 million ping count for 3 minutes. And this is also the real world example from RayServe. RayServe is a machine learning model serving library written on top of Ray. You can see it creates 3 different custom metrics like request counter, error counter, and also queuing latency tracker. So they can actually track these metrics. And this is how to record metrics. As I showed you, you just need to specify the value with the .record method. And we also provide the custom labels, so you can actually label your metrics at the same time. Let me briefly explain what's happening behind the scene. Once metrics are recorded through the custom metric API, all the metrics will be collected and processed in open census formats by Ray. And after that, they'll be available through Prometheus endpoints. We'll go through how metrics are collected at the end of presentation in the architecture diagram. So let's see the last solution. To provide a way to track down traces of distributed task connectors, Ray will also have distributed tracing support. This is something that is not currently in progress, but we are actively, this is currently in progress, and we're actively developing it. And sooner or later, it'll be available from Ray. Distributed tracing is a way to collect stats grouped by the same span ID. And this is particularly useful for Ray's programming models that use actors and tasks, because it is really hard to know the trace of actors and tasks when you're running the application. And actually, Anyscale backend is already using open telemetry tracing on top of Ray. So we are already collecting this distributed tracing, and we are actually able to see all the trace information from our dashboard. So this is what we are doing in our product. This is for our production monitoring systems. So this is not provided users, but this will be available for users sooner or later as well. Let's dive into the next topic. Ray is also object-based programming. Let's take a deep dive into Ray objects. First, Ray's tasks and actors exchange data through immutable objects stored in shared memory. Tasks and actors are basically able to access these objects to pass data to each other. And second, to make it easy to manage memory usage of objects, Ray is supporting distributed reference counting for the sake of automatic memory management. And this means objects that are not used by Ray will be automatically cleaned from the cluster. So this is the demonstration of what I just said. So let's say there are 2 tasks, 1 actor, and they're mapping many-to-many mapping to 3 objects. This is the corresponding code. You can see there are 3 objects created and also 2 tasks, task A and task C. And in the middle, there's a task B. So this is exact same code that presents the previous diagram. Let's suppose task C is done earlier than other tasks. And in this case, the reference to object 3 is fully gone, and object 3 is garbage collected. This is how all the Ray objects are automatically managed. Then what's the challenges in this programming model? The most common issue is memory leak. And although Ray implemented distributed reference counting to make the memory management as easy as possible, users still can have memory leak. For example, imagine you just forget to have a local reference to one of your object reference. In this case, the object won't be garbage collected forever until you remove the references because it's still used. And in order to solve this problem, we wanted to improve the visibility to Ray object references. And we developed one client tool and also dashboard called Memory View. This is how Memory View looks like. As you can see, it has various information about objects and where they're referenced. And most cool stuff is it shows the call site, so you can actually know where the objects are created. So I'm gonna have a short demo about how to debug real world issue. So this is the real world issue that I was reported about 19 days ago. The user claims that there is always out of memory issue when he was running the applications. And this was the code example he gave me originally, and he also gave me the more toy example. So what I did is I just copied and just started this application. And I just went to the dashboard, click the memory view. And from here, you'll be able to see the total used by pending test count is keep increasing. And this is why there was memory leak. And let's actually reason about why this happens. So when you actually just look at code, this object ID is the reference is gone every time the loop is done, as you can see, which means this object ID has to be garbage collected. So this is an example. So this is our guess. Every for loop, we just expected the object was garbage collected. But in reality, it wasn't. We could see that the pending task count has been increased. And the reason behind is because we submitted so many call tasks very quickly. So all the call tasks has been queued in the Rayleigh queue. And because objects are referenced by them, although their local reference was gone, their distributed reference counting wasn't gone yet. And as a result, the object was still not garbage collected. And we could be able to see this by actually check the reference type of the object, and which was used by pending tasks. And I really quickly figure out this issue and told users that you just need to make the call task a little bit more heavier so that you're not going to submit too many tasks at once. And in that case, you can avoid having too large memory in the short time. So the next topic is the observability of Ray itself. We're going to actually make it very short because we are kind of out of time. But since Ray has really highly distributed infrastructure, it has just typical problems that most distributed systems have. Like there are too many components, you don't know what they're doing, and there are a lot of logs, and logs are all across, so it's hard to have a trace of logs. There are various solutions we provide to make it easy to debug and observe the Ray system itself. And as I mentioned earlier, if it is easy to debug Ray system itself, you're going to save a lot of operational costs because you can just operate a single system instead of operating multiple complex glue systems. And we basically provide 3 different solutions. One is dashboard machine view, and also system metrics export, and also event framework. You'll be able to see this information later more in our documentation. So lastly, let's see the evolution of Ray's monitoring architecture. We'll see Ray's architecture has changed before. We'll see how Ray's architecture has been changed before and after 1.0. So there are 2 motivations of architectural change. So we figured out some users turned off the dashboard because of overhead. So we wanted to minimize the overhead in general. And also all of Ray users have their own monitoring stacks, which means our solution, which is making the dashboard the first-class citizen for monitoring, was not working for most of users. So we just wanted to make dashboard as one of consumers of the whole monitoring infrastructure. So firstly, let's take a look at the architecture before 1.0. So here, before 1.0, after 1.0, they're not exactly the right diagram because this architectural change is in progress. So just be aware of that. The diagram represents the common architecture of Ray. It has many worker nodes and a head node, which has the dashboard process. And so let's see what's happening. So every 1 second, dashboard pings the Rayleigh. And after that, Rayleigh pings all the workers to get the states. And Rayleigh respond with its own protobuf format. So dashboard can get the stage of the each node and each worker. And this happens to every node in the cluster every 1 second. And this actually incurs really high overhead because Rayleigh is on the critical path, which means Rayleigh is code that we are running for some of Ray APIs always have to pass Rayleigh. And since Rayleigh becomes busy by collecting metrics, the system started having overhead and the whole things became a little slower. So let's see how the architecture has been changed after 1.0. As you can see, there is an additional process called dashboard agent at each node, and dashboard agents are Python processes running at each node. And this is in charge of coordinating all metrics, logs, and tracing from each node. So this is what's happening now. All the Rayleigh and workers are reporting to metrics agent, and metrics agents process all the telemetries. So now dashboard requests data from the dashboard agents, and this is happening on demand. In the same way, it requests to every node in the cluster. After that, dashboard will expose the API, so the users are actually able to consume data from the dashboard. And note, this is also not done yet. This is currently in active progress. Let's take a look at the advantage of new infrastructure. The first advantage is the low overhead. As you can see, we excluded Rayleigh from the metrics collection path, and everything's done within a single process called dashboard agent. And thanks to that, we had much less overhead than before. And also dashboard stay relatively lightweight because we are pulling data only on demand. And the second advantage, the biggest advantage, is we can decouple monitoring infra from the dashboard. And dashboard is just one of the consumers of the infrastructure. So let's see the example. The box means the metrics infrastructure, and agent and edge node collects and processes telemetry such as events, metrics, or custom metrics, or things like that from each node. And as you can see, dashboard is just one of consumers. And in the same way, you can set up the Prometheus as another consumer, and that's how we actually collected metrics, custom metrics, and system metrics through Prometheus, as I show in the beginning of the slides. We can use many other industry solutions for logging, metrics, tracing, and etc. as a consumer of the infrastructure as a result. So lastly, let's see the future roadmap. At the point of 1.0, we are moving towards new architecture, and the metrics pushing to the agent is already implemented. And we are supporting importing metrics using Prometheus, and also dashboard UX has been improved a lot. And we also started having experimental custom metric support. And after 1.0, we are also going to have dashboard, official dashboard APIs the users can consume. And we are going to support custom events and also distributed tracing. Of course, there will be more improvement in dashboard UX. We are investing a lot of resources on it. And also the architecture change is gonna be finished up. So in conclusion, improving monitoring and debugging experience in Ray is crucial to achieve our goal. And we are in active progress in building necessary tools to make it really easy. That's it. Thank you so much for watching the presentation.